So the goal of our current session is not to really review specific statistical methods, but rather to focus on how assumptions in general shape whether your results are actually interpretable or defensible. Every model that you have is going to have a different set of assumptions. So the way that I'm approaching this today is to really understand the importance of assumptions and cover some of the key ones that we see a lot, especially the ones that are connected to multiple regression, or also known as ordinary least squares. So we'll be spending the next hour looking at how to diagnose assumption issues early, how to evaluate whether they matter, and how to make some informed analytic decisions from there. As Jessica said, please feel free to drop questions in the chat as we go, and we'll have some time at the end to discuss or to go over everything. Just to give you a sense of who I am, I got my PhD in 2015 from Purdue University in political science, focusing on public policy, political psychology, environmental policy, of that really interdisciplinary kind of stuff. And my background is strongly in research design, statistical analysis, and applied policy research. For the past several years, I've worked closely with doctoral students with a dissertation coach, and I work with students that are across a wide variety of disciplines, supporting them through the analysis phases of their dissertations. And a big part of my work is helping students move from, I hit the wrong button, sorry, from running models to actually understanding and being able to defend the analytic decisions that are made. So our objectives for today, by the end of this session, the goal is for you to be able to approach assumptions a bit differently than how I feel like they're oftentimes taught. First, we're going to assess how your research question data and model assumptions fit together. You're going to be able to diagnose assumption violations and, more importantly, understand what they actually do to your results. Third, we're going to make some informed decisions about when assumptions aren't perfectly met, which is pretty much almost always the case in real research. And finally, we're going to be able to justify our decisions clearly, because at the dissertation level especially, that's really what distinguishes strong analyses, is your ability to justify the decisions that you make. So here's how we'll spend our time together today. We'll start by clarifying what assumptions actually do, because as I already said, they're oftentimes taught as a checklist rather than as something that actually shapes interpretation. Then we'll walk through some core assumptions that we very commonly see in statistical research, and more importantly, why they matter for your results. From there, we'll focus on how to diagnose violations in practice and how to think about what those violations actually mean. And then we'll shift into how to respond. So how to make decisions that are defensible, even when your data aren't perfect. And finally, we'll apply all of that in a short case example before we wrap up and I take questions. So as I already said, up to this point, assumptions are often taught, in my view, as something that you check off after. A lot of times I see students and clients often running their assumption tests after they even do all their statistic testing. Like, I've had people come at me once they've already written up most of their chapter 4 and be like, oh, my advisors want me to do assumption tests. Well, no, the assumption tests actually come much, much earlier than that. So for the rest of this session, I want you to think about them not just as something like that's on a checklist, but assumptions are actually what determine whether your results actually mean what you think that they mean. So this section is all about reframing assumptions, not as a procedural step, but as the foundation for interpretation. So what actually is an assumption? When most people are taught assumptions, they're a checklist. But I want to reframe that. An assumption is actually a condition that is required for interpretation. It is those elements that need to be true in order for a statistical model to produce results that actually mean what you think that they mean, what they are purported to mean. So the question isn't just, can I run the model? Will the statistical package actually work and produce results? Instead, it is, can I interpret the output in a meaningful way? That's why assumptions are really the foundation of valid inference. Everything that you conclude from your model depends on these assumptions holding up to at least a reasonable degree. So once we think about assumptions as conditions for interpretation, our next question becomes, what is it exactly that they affect? Why is it that they matter? And there are three main things when we're thinking about our output that assumptions are really governing. First, the assumptions have a strong effect on our coefficients. So are the estimates actually actually capturing the relationship that you think they're capturing? If assumptions, especially something like linearity, fail, then the coefficient that is produced and how we think about substantively interpreting what that coefficient represents may not actually stand up. It may not actually represent the relationship accurately. Second, assumptions have an impact on our standard errors. This is what determines what our p-values are and what our confidence intervals are. If in assumptions like independence of observations or homoscedasticity fail, then our significant tests may not be valid. They may overinflate our standard errors, or they might artificially reduce or shrink our standard errors, right? And third, our assumptions can influence our model fit more broadly. So does the model that we have selected actually reflect the structure of the data that we have in practice? Or are we trying to force a model and like shoehorn data into a model that it's really not meant to capture, that's not meant to capture well? So assumptions are really determining whether these core pieces of your output are actually trustworthy. And this leads to a really important point. The same output does not necessarily mean the same thing if the assumptions do not hold up. A model can totally run, you can get coefficients, p-values, r squared, pseudo r squared, whatever. But the interpretation of those results can be very, very different depending on whether the underlying assumptions are actually reasonable or are reasonably met. So just kind of to put a finer point on this, as an example, on the left, we've got on this slide, we've got two scatter plots, right? On the left, the assumption of linearity fits. On the right, it doesn't. On the left, the assumption is very much linear. The spread is relatively consistent, and the model is actually capturing the what is going on in the data, right? There's a little bit of noise, a little bit of variation that's there, but if you can actually see, there's a line of best fit that is drawn, and everything follows. So when we get our coefficient, when it said, following that a unit change in X leads to a coefficient change in Y, that actually fits. On the right-hand side, the model will still run, but the underlying pattern of the data are different because there's a curvilinear relationship that's here, right? So there could be a curvilinear relationship, there could be changing variance, or both. And the key issue here is that the model is now forcing a linear summary onto something that isn't actually linear. So when you say that, oh, there's a coefficient change in Y, that doesn't actually hold up. It doesn't actually describe what is going on. So even though the statistical output might look similar, the meaning of the coefficient is not going to be the same because a pattern was forced onto data that it doesn't actually reflect. In one case, it's actually describing the relationship, and the other, it's just averaging over a pattern that it doesn't actually capture. So the issue isn't whether the model runs, but it's whether the result means what it is that you think that it means, and then the implications that means for your interpretation. So now that we've reframed what assumptions are, the next step is to think about where they actually come into play in your analysis. Instead of treating them as something that you check at the end, we're going to look at how they shape decisions throughout the entire process. So assumptions don't just evaluate your model, they're embedded through the entirety of your data analysis. Before you actually engage in your modeling, they're already shaping what models you determine to even be appropriate. When you choose a model, you're implicitly accepting a set of assumptions about your data, what your data look like, and about your actual question and whether you've checked them yet or not. During your modeling, diagnostics are essentially testing whether your choice stood up, whether what you thought about the data actually was accurate. So you're asking, is the data consistent with the assumptions that I have already committed to? And if they're not, then we need to make some kinds of adjustments. After you engage in your modeling, and this is where it matters most, because assumptions determine whether your results are actually interpretable, not whether you can report them, but whether you can trust them. So the key shift here is that assumptions aren't something that you just check and verify at the end, but they're something that are embedded throughout the process and that you think about throughout the entire process. So you're committed to them from the moment you choose a model. Before you run anything, this is the question that you should be asking. Do the assumptions of this model actually make sense for my question and for my data? You start with the question, what are you actually trying to estimate? Are you trying to say that there's some kind of linear relationship? Are you trying to explain some differences between groups? Are you trying to explain something that is a little bit more complex? That is going to determine what kind of model it is that you are needing to adopt, and along with that, what assumptions are relevant for that specific model. You then look at your data, think about how you've measured your data. What is it that you actually have? What is the scale? What is the distribution? What is your sample size? Is there any clustering or any other weird or interesting features about the structure of your data? That too is going to affect the type of modeling that you adopt. And you select your model based on your design decisions. Then your model, what does it assume? What does it assume has to be true in order for the model to stand up? For something like OLS, or also known as multiple regression, we've got things like linearity, independence of observations, consistent variance, so on and so forth. The key is that these elements need to align. If they don't, you're building your analysis on assumptions that don't actually fit the problem. And all of those issues are just going to snowball and compound once we get to the point of interpretation. And that really is where a lot of dissertation issues start. It's not necessarily in the diagnostics, but in our initial model choice and our awareness of what that means for our dissertation. So the big four, these are some core assumptions. They really strongly relate to multiple regression, OLS, and because that really serves as a root, as a foundation. I do have to note that there are a lot of other assumptions that exist for more basic bivariate analyses, as well as for more advanced statistical analyses. And so that's why I want to focus more on the theory behind a lot of this stuff. You need to know what the assumptions are based on the model that you have selected, not necessarily, oh, these are just four things that I know I always have to check on, because you don't always have to check on these, but these do tend to be some of the most common ones that we see and that we talk about. So these are the core assumptions that a lot of common models rely on. But what matters is not just what they are, but what it is that they do to your results. So first, linearity is about whether your model is capturing the actual form of the relationship between variables. If this fails, your coefficient may be summarizing the wrong kind of pattern. Independence is about whether your observations are actually providing separate pieces of information, or if there's some repetition that's involved. If this fails, then your standard errors are oftentimes going to be too small, and the results can look more significant than they actually should be. Homoscedasticity is about the stability of variance. If this one fails, then your inference, your p-values, confidence intervals, everything becomes a lot less reliable. Finally, normality. When we're talking about normality in terms of linear regression, it is about the distribution of the errors. And it mainly affects inference as well. But a lot of times this assumption can be overemphasized relative to the others. And people will look at normality, but they won't necessarily look at, say, linearity. Especially in larger samples, people tend to overemphasize this. The key point, though, is that each assumption affects a different part of the output. And so when something goes wrong, you need to know what the assumption is or what part of your results is actually impacted. So why do these matter? So the reason that we care about these assumptions is not because they're rules, it's because they determine whether the key parts of our output are actually trustworthy. So first, for our coefficients, are they actually capturing the relationship that you think they're capturing, or are they distorted? Do they provide a distorted picture of what's going on because the model doesn't actually fit, doesn't actually reflect the data? Second, our standard errors. This, again, is what drives our p-values and our confidence intervals. And if certain assumptions fail, our results are going to look more or less significant than they actually are. And third, our conclusions, because ultimately, when you write up your dissertation and what you write up in your dissertation depends on whether those first two pieces are actually valid. So even when the output looks clean, looks nice and wrapped up in a pretty bow, the interpretation might not actually be. The important part is that the output itself doesn't tell you whether these things are trustworthy. It relies on you knowing what it is that you have to examine and from evaluating those assumptions. Up to this point, we've been focused on what assumptions are and why they matter. Now we're going to shift a little bit more to the practical side. So how do we actually detect when assumptions don't hold in the data? This is where diagnostics come in, but the goal isn't just to run tests, it's to understand what the data are telling you. So we'll walk through each of the big four assumptions that I noted before and how to diagnose each one of these in practice. Something else that's important to note is that some assumptions you are able to evaluate statistically, and some of them are really more oriented toward design. And so you really need to be able to understand and differentiate between, okay, what do I run a test for, and what do I need to be conscious of at the point of design? Okay. So the first one that we talked about is linearity. We've already talked about this a number of times. But linearity is about whether a straight line model actually represents the relationship that exists within the data, or if there is some other kind of curvilinear relationship that exists. It doesn't mean that the data have to form a perfect line. Instead, it means that a linear approximation is actually reasonable. So what you're looking for here are patterns. If you see a curvature in a scatter plot, or in residuals, that's a sign that the model isn't actually capturing the relationship correctly, and some kind of data transformations may actually be necessary. What actually happens then is the coefficient that you get is essentially averaging across a relationship that isn't exactly linear, and it could just be completely off. There could be suggesting some kind of a consistently positive relationship where it's not actually consistently positive. There could be a number of things going on, and that all of that kind of information gets lost. And there's no way that your model is going to tell you that that's what's happening. It's something that you specifically have to look for in advance. Practically, this is why visual diagnostics matter a lot more than formal tests for something like linearity. You're looking for structure in the data, not just statistical significance. So we have to run these kinds of scatter plots, develop these scatter plots, especially for our key hypothesized independent variables against our dependent variables. If linearity fails, the issue isn't just fit of the model, it's that your coefficients won't mean what you think that they do. Independence is another one, as we already noted. And oftentimes, this one can be the most serious and most overlooked assumptions. In some ways, this assumption is one that is design choice, um, because a lot of times we think about the independence of observations as being, oh, is this an overtime or is it a cross-sectional kind of analysis, right? But there's other ways that the independence of observations are able to be violated, um, aside from just having the temporal consistency there. Um, it's not something that you usually are able to see in something like a scatter plot, but it's really about how the data are collected. In practice, violations usually come from structure. So we'll oftentimes see something like clustering or repeated measures. So repeated measures is where you have over time analyses. You're collecting the same data from, or you're collecting data from the same unit over time. Or we could have clustering. So something like collecting a number of data points from one state within one state, and then another state, or what have you. And there's things that are common within those clusters, right? So for example, students within the same program or multiple observations from the same individual over time. If observations are related, you're effectively treating similar data points as if they were independent pieces of evidence. When independence fails, you're effectively counting the same information multiple times, and your sample looks larger and more informative than it actually is. What that does in practice is it shrinks your standard errors and leads to standard errors that are too small and makes the results look like they are more statistically significant than they actually are. In this case, we are also able to use statistical tests to help to determine whether this assumption has been violated or not. We use a Durbin-Watson test when we have ordered data, or we use an ICC to examine clustering. But these kinds of tests are secondary. Our structure oftentimes and our data collection procedures oftentimes determine whether there's dependence or implied dependence, and if that could be a potential issue. This isn't just a minor technicality. Violations of independence can fundamentally change the conclusions that we are able to draw from the data that we have and from our results. Another important assumption that we have is homoscedasticity. This assumption is that the variance of errors within the model is consistent across levels of the predictors. When heteroscedasticity is present, the spread of the residuals is not constant, or I'm sorry, when heteroscedasticity is present, the spread of the residuals is not constant. You often will see some kind of a funnel or a fan shape where the variability increases or decreases across the range of the data. The way that it was explained to me when I was in grad school is you want to be able to visualize kind of like a shrapnel from a shotgun kind of thing. So in the top plot that we have over here, this is where we see that homoscedasticity exists. Everything's kind of random all over the place. Where we have heteroscedasticity, so the assumption is violated, we see that there are patterns within the data that we don't, or within the residuals that we don't necessarily want. The main diagnostic here, we look at scatter plots of the residuals versus the fitted values. You're looking for whether the spread is roughly even or whether it changes systematically. There are formal tests like a Bruch-Pagan or a White test, but the visual pattern is really the standard that we tend to use, and it usually is more informative than just using the statistical tests. This assumption largely affects your standard errors. So your coefficients very well may be fine, but your p-values and your confidence intervals may be unreliable. So when heteroscedasticity is present, the issue isn't the estimate per se, but it's your confidence in that estimate. We usually address this kind of violation by using robust standard errors in our model as opposed to just letting the model run normally. Heteroscedasticity doesn't usually bias your coefficients, but rather it distorts the inference. And finally, we're going to talk about diagnosing normality. This assumption, okay. When we're talking about regression analysis, this assumption is about the errors or the residuals that being normally distributed, not the raw data, not the raw variables. So when we run our analysis, we have to reserve the residuals and then look at and examine those residuals. When normality is violated, you'll see skewness or heavy tails in the residuals. So you can look at your skewness and kurtosis to determine your normality. But we also really like to use visual tests here, and we'll run like PP plots or QQ plots that show up as points deviating from this diagonal line. There are formal tests like a Shapiro-Wilk test, but these tests can be very sensitive, especially in larger samples, and often will flag minor issues that don't really matter. So that's really one of the reasons why we tend to focus more so on our visual representations. So here, the top one, the assumption of linearity is met. You want all of these points to be falling on the diagonal line. In the bottom one, linearity is not met. We've got a lot of deviation off of that line, right? Violations of normality primarily affect our inference, our p-values, our confidence intervals. It generally does not affect the coefficients themselves. So this assumption is definitely important, but a lot of times it's overemphasized relative to the other assumptions, or it's maybe not that it's overemphasized, but is emphasized so much, and a lot of other ones are so ignored that it seems disproportionate. But the OLS can stand up to some deviations of normality. So in many cases, especially with moderate or larger samples, small deviations from normality are not a major concern, whereas they might be for smaller samples. The key here is to focus on whether the violation meaningfully affects our inference, not just whether it exists or not, or what that pattern actually looks like. So far, we've focused on identifying assumption violations. But a more important question is, what do you do once you actually find them? Because in real data, you will almost always have some kind of violation. So in this next section, it's about moving forward from diagnosis to decision, how to evaluate those violations, determine whether they actually matter for your results, and how to decide whether your analysis is still going to be defensible. Once you've identified a violation, the next step is to evaluate it, not just to note that it exists, but you have to make a conscious choice of how are you going to deal with it. First, we want to evaluate how severe it is. Is there a minor deviation in the pattern, or is there a substantial deviation? How big is the violation? What does the violation affect? Does it impact the coefficients? Does it impact the standard errors, or both? This is going to tell you how serious it is for the violation is for your interpretation. Does the violation actually change your interpretation? What can you claim based on the results? How much is it going to have that kind of impact? What's the value added to making some kind of a deviation or to changing your approach? Then you need to decide, once you've answered those questions, you then need to decide, based on your evaluation, what to do. Do you just proceed as is, say that these violations occurred if the impact is minimal, and note that the impact is going to be minimal, and say in your dissertation why? Or do you need to adjust the model? Do you need to do something like, as we talked about, if you have heteroscedasticity, throw on robust standard errors? If you have a curvilinear relationship, do you need to do data transformations. Do you need to take the log of something? Do you need to throw a square on something, right? Or do you need to specify something differently? Do you need a total different model specification? Or do you need to reconsider your approach entirely if the violation completely undermines the model? The goal here is not necessarily to address and to eliminate every violation. It's to make a reasoned, defensible decision about how to proceed, especially given the constraints that you have, right? There's always something more you could do. There's always something additional you could learn based on what it is that you know about your program, your advisor's knowledge, preferences, your own skill set. What is considered to be reasonable and what is it that you're able to justify to do? So next we're going to talk about some common dissertation mistakes and where I see a lot of the violations of assumptions leading to problems in dissertations. These are patterns that I see pretty consistently in dissertation work, not necessarily because students don't know the material, but because they're not necessarily sure how to apply it. So as we've talked about already, a lot of times people will treat assumptions as a checklist. That they will check after the model runs rather than use as a guide for model choice and for adaptation. A lot of times people will rely on software defaults. And I think part of this is also the way that some statistical packages are structured. So as an example, a lot of people in various fields of the social sciences especially use SPSS, and assumption tests are run as part of the model being run. And so it seems like something that happens at the same time, or that you just note as you're writing your results up, as opposed to something that you're supposed to be responsive to during your analysis process. So there's features of the software that make it seem like assumptions are playing or supposed to play a different role than they actually are meant to run. But also, a lot of times people think if the model runs, then it's okay, right? That the assumptions, if an assumption is not met, that the model will completely implode and it won't run. That's not the case. So if the software won't tell you whether the model is appropriate or not. These assumptions are about appropriateness and trustworthiness, not about whether a model will actually collapse or not. A lot of times people can overreact to relatively minor violations and will spend a lot of time trying to fix small issues, especially something like normality, that don't materially affect the results. So they can kind of over exaggerate what the impact of some assumption violations are and just fall down a rabbit hole of addressing violations. But at the same time, we can have people who are ignoring serious violations, particularly things like independence of observations or non-linearity. So what the structure and the pattern of the relationship is like. These are issues that will actually undermine the inference, actually undermine the interpretation and our ability to say what the relationship between variables are. Sometimes people will report results without justification. They'll present results as if everything was totally fine. Either they won't note that they did any assumption testing at all and just ignore if there are assumption violations, or they'll note that there were violations, but then just proceed as normal without explaining what was checked or how any decisions were made about how to proceed. So in most cases, the issues aren't really technical, but it's instead about judgment and how assumptions are being treated and being used in the analysis. At the PhD level, it's really important for people to remember that the question isn't just what you ran and what was produced, but whether you can actually defend it, whether you can actually justify the choices that were made. So far, we've talked through some assumptions, diagnostics, and how to evaluate violations. Right now, before we wrap up, we're going to put that into practice with a short case example. The goal here isn't to do a full analysis It's to walk through how you would think about assumptions in a real dissertation scenario. So as we go through it, I want you to focus on three things: what the output suggests, what the assumptions reveal, and how you would decide to proceed. So to set up for the case, this study is looking at the relationship between stress and maladaptive coping among graduate students. In terms of the data structure, we have a relatively small sample, around 60 observations, with multiple measures of stress. So a fairly typical survey-based dissertation data set. It's based on self-reported survey data that was collected across multiple cohorts. The student proposed a multiple linear regression with maladaptive coping as the outcome or the dependent variable, and a variety of stress variables as their predictors. On the surface, this looks completely reasonable. There's a continuous outcome, multiple predictors, just a fairly standard approach. So the question is, before we even look at results, what assumptions are we relying on? And do they actually make sense for this setup? The output is telling us that the model is statistically significant. So at a basic level, it looks like the predictors are explaining variation in maladaptive coping. We're also explaining a reasonable amount of variance, around 35 to 40%, which in many dissertation contexts would be considered solid, totally fine. We have at least one predictor that appears statistically significant and maybe another that's marginally significant. The rest are non-significant, which is also very typical in this kind of a model, especially given the size of the data set. So if you saw this in a dissertation, nothing here would immediately raise concerns. It looks like a standard interpretable regression result. But when we look at what the assumptions reveal, there's some questions that are brought to mind. On the slide, in the coral colored box, I've got listed the core assumptions of OLS. Some of these we talked about. They're part of the core ones, the core ones that we talked about. But there's also some additional assumptions, such as there's no multicollinearity and no omitted variables. It's important for us, again, to know what the assumptions are of each specific model so that we are tailoring and we are looking at the assumptions relative to that model, not just a preconditioned set that we look at. So I have listed the OLS assumptions, and these are the conditions that we are relying on when we are interpreting our output. And importantly, nothing in the regression itself tells us whether these assumptions hold. So like I said, we have to look at these ahead of time. So looking at the assumption results, I'm not presenting a bunch of tables and everything here just for the sake of space. In terms of linearity, if the relationship wasn't actually linear, we found that the relationship wasn't actually linear. If the relationship isn't actually linear, then the coefficient may not represent the relationship accurately, and it's summarizing something that the model just isn't capturing well. And in this case, we had a curvilinear relationship where there was an exponential relationship. So we needed to actually transform the data. We found some heteroscedasticity. This meant that the standard errors were not going to be reliable, and so the significance that we saw could be misleading. Another concern, and this is based on the design of the data, or of our data collection procedures, there was a potential for clustering. And if the observations are clustered or dependent with one another, then we may be overstating how much independence actually exists within the information that we have, which again can affect inference. So even though the output looked clean, each of these issues changed how we were able to interpret those same numbers. Again, the assumptions don't change the output, they change what the output actually means. So the question now becomes, given these potential issues, how do we decide on whether this model is still usable? So in making that determination, the next step is deciding how to respond. The first step is to clearly acknowledge what it is that's going on. In this case, we have nonlinearity, heteroscedasticity, and we have some concerns about the independence of our observations. Importantly, when we're doing our write-up, we are not ignoring them and we're not overstating them. We want to be very honest and we want to be precise. Then we want to make adjustments where it is that is appropriate. We decide if they're actually needed based on the severity, and that could mean changing the specification, using transformations, or applying something like robust standard errors. In this case, what I ended up having to do, because of what the data looked like, we were not able to deal with the clustering issue because that would have involved doing engaging in a model that we just didn't have the data for. Right. So we threw some robust standard errors on there, and we did a data transformation to deal with the nonlinearity issue. Next, we want to interpret cautiously. We scale our interpretation and the kind of language that we're using for our interpretation to match the strength of the model. So instead of making broad claims, we focus just on what the model is able to reasonably support. And we use a tone where we're noting that we have to take things with a certain grain of salt. And finally, we justify our approach. And this is really the key step, being able to explain our decisions, not just making them. So why we proceeded, what is it exactly that we adjusted, and noting very clearly what limitations actually remain and what we need to be conscious of. So a defensible decision isn't about having a perfect model, it's about having a reasoned and transparent approach to the model that we're actually using. And this is what distinguishes strong dissertation work. You're not wanting to have something that is necessarily completely clean and absent of issues, but it's about how we handle those issues and how we're addressing them and demonstrating that we understand what the implications are. So to pull all of this together into a simple process that you can actually use, step one, we need to clarify and identify the model and the associated assumptions of the model. We want to start with being explicit about what assumptions the model is making, not just the tests that you're running, but what has to be true for the tests to be determined to be appropriate or not. We want to run our diagnostic checks to see whether your data are consistent with those assumptions. Then we want to evaluate those assumption tests. How severe is the issue and what part of the results does it actually affect? Finally, based on that, we want to decide how to proceed. Do we need to adjust the model? Do we need to reconsider the approach? Do we need to engage in any kind of data transformations? And finally, we need to justify what our approach is. We don't just make changes. We don't just make adjustments. We need to be able to clearly explain and defend that decision in our text. And this is really what a strong analysis looks like. It's not about having perfect data. It's about making informed and defensible choices. So to just kind of wrap up some key takeaways, there's a few core ideas I just want you to leave with. First, assumptions are conditions for our interpretation. They're not a checklist. They determine whether your results actually mean what it is that you think that they mean. They tell us how trustworthy our output is. Our model output alone is not enough. You cannot solely rely on coefficients, p-values, adjusted R-squareds, or what have you. Diagnostics are what tell you whether those results are actually trustworthy and how much faith we can have in our results. Not all violations matter equally. They're not all the same. The goal isn't to eliminate every issue, it's to understand what issues actually exist and which ones actually affect your conclusions. Strong analysis requires justification, and ultimately, what distinguishes a strong dissertation is your ability to explain and defend your analytical decisions. So if you take one thing from this session, it's this. You're not just running a model, you're making and defending an argument. Everything needs to relate back to what is the core of what you are meant to be doing. We need to make sure that how we are modeling things reflects what our underlying ideas are, and that we're not just following a preset plan, but we are actually being responsive to the data that we were able to collect. Thank you very much.